Tonight, we're going to talk about the cold emptiness of space. But not the kind of cold you feel stepping outside on a January morning with your coffee. Not the kind of cold that makes your car engine groan before it starts. We're going to talk about a cold so complete, so deep, and so absolute that it makes every experience of cold you've ever had in your entire life feel like standing next to a bonfire. We're going to talk about the cold of space. And before we get into this, if you've ever found yourself lying awake at night, wondering what's really out there, take a second to like the video or subscribe. It's a small thing, but it helps this channel find more people who actually want to know how the universe works. Now, let's get into this. Most people think they already understand this topic. You've probably heard it your whole life. Space is cold. Space is a vacuum. If you went outside without a spacesuit, you'd freeze instantly. That last part, by the way, is wrong. And that's exactly where we're going to start, because almost everything the average person believes about the cold of space is either incomplete, misleading, or just plain backwards. By the time we're done tonight, you're going to see something you look at every single night in a completely different way. Not because we're going to throw dramatic music at you and tell you to be afraid, but because the actual truth, the real physics of what cold means in space, is so much stranger and so much more specific than the version you were handed in school. So, let's start at the very beginning. Let's start with the question that almost nobody actually asks. What does it mean for something to be cold in the first place? When we say something is cold, what we're really describing is the average speed of the particles inside it. That's it. That's the whole thing. Temperature isn't a substance. It's not a thing that exists by itself floating through the air. Temperature is a description of motion. When particles in an object move fast, we say it's hot. When they slow down, we say it's cold. Put your hand on a cold piece of metal, and the metal feels cold because the slow-moving particles in the metal are pulling energy away from the faster-moving particles in your hand. Heat flows from where particles are moving quickly to where they're moving slowly. That's always the direction, always. And this single fact is going to become very important in a few minutes because it explains one of the most counterintuitive truths about space that almost no one ever talks about. Now, here's what most people don't realize. For heat to move from one object to another, you typically need one of three things. You need conduction, which is direct contact between two objects, like that cold metal under your hand. You need convection, which is a fluid like air or water carrying heat from place to place, like the warm air rising off a radiator. Or you need radiation, which is heat travelling as electromagnetic energy, the way you feel the warmth of a fire on your face without touching it. In space, you don't have conduction because there's nothing to touch. You don't have convection because there's no fluid, no air, no medium to carry heat around. The only way heat moves in space is through radiation. And that one fact changes everything about how you have to think about cold up there. Let's set a number on the table so we have something real to work with. The average temperature of space, the background temperature of the universe itself, is about 2.7 Kelvin. That's negative 270.45 degrees Celsius. Or if you use Fahrenheit, negative 454.81 degrees. That's not a typo. Negative 454 degrees Fahrenheit. The coldest temperature ever recorded on Earth's surface was in Antarctica, at a place called Vostok Station, where in 1983 the thermometer hit negative 89.2 degrees Celsius, which is about negative 128.7 degrees Fahrenheit. Take that number and understand that the background temperature of space is still more than 3 times colder than the coldest place ever recorded on our own planet. It's not a little colder. It's not even twice as cold. Think about the most extreme cold you have ever personally witnessed or read about. The kind of cold that kills engines, shatters metal, makes rivers freeze solid. The universe runs almost 200 degrees colder than that. But here's the thing we need to slow down and actually understand. That number, 2.7 Kelvin, is not just an average taken across a few star systems. It's not a local reading from one part of the galaxy. It's the temperature of the entire observable universe, measured in the gaps between everything, measured in the spaces that have no stars nearby, no planets, no gas clouds, nothing but the faint hum of energy left over from the very beginning of time. We call it the cosmic microwave background. And we're going to come back to it because it's one of the most extraordinary things in all of physics. And most people have never heard the actual story of what it is. But first, let's stay with this number for a moment. 2.7 Kelvin. The Kelvin scale doesn't use degrees in the normal sense. It starts at 0 and goes up. 0 Kelvin is the lowest temperature physically possible. It's the point at which particles theoretically stop moving entirely. We call it absolute zero. An absolute zero is 273.15 degrees below the freezing point of water. So 2.7 Kelvin is barely, just barely, above the coldest thing that could ever exist. The universe isn't just cold. The universe is almost as cold as it is physically possible to be. Now let's think about absolute zero for a second, because it's genuinely one of the strangest ideas in all of science. We said temperature is the average motion of particles. Absolute zero is the temperature at which that motion completely stops. But here's the catch. We've never actually reached it. Not once, not even close. The coldest temperatures ever achieved by humans in a laboratory are around 1/10 of a billionth of a Kelvin above absolute zero. That's 0.0000000001 Kelvin, which is so close to zero, it sounds like we basically got there. But in quantum mechanics, you can never fully reach it. The uncertainty principle says that if a particle stopped moving entirely, we'd know both its position and its momentum perfectly. And that's not allowed. At the most fundamental level of reality, particles always retain what physicists call zero-point energy. Even at the coldest possible temperature, something is still moving. The universe keeps a tiny, irreducible tremor in everything. And we should stop here for just a second and let that land. Because what we're saying is that perfect, cold, absolute stillness is physically impossible. Not just technologically difficult, not just practically unachievable, actually impossible. Built into the laws of physics is a rule that says nothing can be perfectly still. The cold of space comes within a fraction of a degree of the coldest thing that can exist. But even the void between galaxies maintains the tiniest possible whisper of thermal energy. Even the emptiest place in the universe isn't perfectly quiet. So why is space so cold? Where did this background temperature come from? This is where the story gets genuinely interesting. About 13.8 billion years ago, the universe began. We don't fully understand what happened in the very first instant, but in the moments that followed, the universe was a dense, unimaginably hot plasma. Not hot in the way your oven is hot. Hot in the way that no atom could exist. Hot in the way that matter itself couldn't hold together. Electrons and protons were free, floating separately in a soup so dense and bright that light couldn't travel through it. Think of it like this. You know how you can't see through a fog? Light scatters off the water droplets and gets lost. The early universe was like that, except the fog was made of free electrons, and it extended in every direction, for billions of light years. Light couldn't go anywhere. The universe was opaque. Then, about 380,000 years after the beginning, something happened. The universe had been expanding and cooling the whole time. And at 380,000 years, the temperature dropped just enough to around 3,000 Kelvin, roughly the temperature of the surface of a red dwarf star, for electrons to finally slow down enough to bind with protons. In that moment, hydrogen and helium atoms formed for the first time. And in that same moment, the fog lifted. Light was free. It shot outward in every direction across the universe in an enormous burst of radiation. That light is still travelling. It has been travelling for 13.8 billion years. And today, because the universe has expanded so much in all that time, that ancient light has been stretched from visible light down into the microwave part of the spectrum. Stretched so much that it corresponds to a temperature of 2.7 Kelvin. That background glow you detect if you point a sensitive radio telescope at an empty patch of sky. That's it. That's the light from the first moment the universe became transparent. That's the afterglow of the birth of everything. Two physicists named Arno Penzias and Robert Wilson discovered it by accident in 1965. They were working with a radio antenna in New Jersey, trying to track satellites, and they kept picking up a persistent, annoying hiss coming equally from every direction in the sky. They thought it was interference. They thought maybe pigeons nesting in the antenna were causing it. They cleaned out the pigeon droppings. The hiss was still there. They tried everything. The hiss was still there. Because the hiss wasn't interference. It was the oldest light in the universe, arriving at their antenna from 13.8 billion years away. They won the Nobel Prize for it in 1978. And today that hiss is one of the most carefully studied signals in all of astronomy, because hiding in its faint variations is a map of the universe as it existed when it was less than 400,000 years old. But here's something we should sit with. That 2.7 Kelvin temperature isn't the temperature of empty space itself. Space doesn't have a temperature the way a rock has a temperature. Space is a vacuum. A true vacuum has no particles, no medium to hold energy. What 2.7 Kelvin describes is the temperature of the radiation field that fills space. The leftover glow. And that distinction matters because it leads directly to the question most people get wrong. If you put a human being in a spacesuit in the middle of deep space, far from any star, what actually happens to their body temperature? Here's what people think. They think you'd freeze instantly, like stepping into an industrial freezer. They imagine the cold rushing in from all sides. But that's not how it works. Because in space, there's no medium to carry the cold to you. There's no air to steal heat from your skin. Conduction requires contact. Convection requires a fluid. The only thing that happens is radiation. Your body radiates heat the same way the sun radiates heat, just at much lower power. You constantly emit infrared radiation. That energy slowly leaks into space, but it leaks slowly. Without air to conduct heat away from you rapidly, you'd actually cool down at a rate closer to what you experience when you sit still in a room with no breeze. It would take minutes, not seconds, for you to start feeling seriously cold. And meanwhile, if you were even mildly close to any source of radiation, like the sun, the side of you facing the sun would get extremely warm, while the side facing away cooled. This is actually one of the great engineering challenges of spacecraft design. Getting too cold is a problem, but so is getting too hot. In low Earth orbit, the side of a spacecraft facing the sun can reach around 120 degrees Celsius, roughly the temperature of water just above its boiling point, while the side in shadow can drop to around -160 degrees Celsius. That swing happens dozens of times a day as the spacecraft crosses in and out of Earth's shadow. The International Space Station experiences 16 sunrises and sunsets every 24 hours because it orbits the Earth roughly every 90 minutes. 16 times a day, it swings through that temperature range. This is why spacecraft are covered in reflective materials, why they have heaters and radiators, why the thermal engineering on any space vehicle is some of the most complex engineering in the whole project. So now we have a clearer picture. Space isn't uniformly cold. It's a thermal patchwork. The empty background sits at 2.7 Kelvin. Near a star, temperatures climb dramatically. The surface of our own sun runs at about 5,778 Kelvin, which is roughly 5,505 degrees Celsius. If you put a piece of steel there, it would vaporize. Not melt, vaporize. The steel would go directly from solid to gas, but travel far enough from any star, far enough into the dark between galaxies, and you sink towards that floor, toward 2.7 Kelvin, toward almost nothing. Now let's talk about something most people have never heard of, and it's going to shift how you think about the word cold entirely. There's a place in our universe that is colder than the background temperature of space itself. Much colder. Not a place we created in a lab. A real natural astronomical object sitting out there in the universe right now. It's called the Boomerang Nebula. The Boomerang Nebula is located about 5,000 light years from Earth in the constellation Centaurus. 5,000 light years. If you could somehow drive there in a car at highway speed without stopping, not sleeping, not eating, just driving, it would take you about 33 billion years. That's more than twice the current age of the universe. You'd still be on the way. The Boomerang Nebula is what happens when a star like our Sun approaches the end of its life. It starts expelling gas at high speed. But this particular star is expelling gas at a rate and speed that is genuinely unusual. The gas is streaming outward at about 164 kilometers per second. That's 590,000 kilometers per hour, fast enough to travel from Earth to the Moon in about 2 seconds. And as that gas expands outward so rapidly, it does something that all expanding gases do. It cools. You've felt this before. If you hold a can of compressed air upside down and spray it, the can gets cold in your hand. The gas inside is expanding rapidly as it exits the nozzle, and expanding gas loses energy. The Boomerang Nebula is doing exactly this, but on a scale that covers light years, and the cooling effect is so extreme that the outer regions of this nebula have a measured temperature of about 1 Kelvin. 1 Kelvin. That's -272 degrees Celsius. Colder than the background temperature of space. Colder than the average of the entire observable universe. This nebula is the coldest known natural object we've ever found. And it's out there right now, 5,000 light years away, as cold as anything can naturally get, shining in the sky of a star that's dying. Think about what that means. The universe itself sits at 2.7 Kelvin. This nebula sits at 1 Kelvin. It's colder than the background it's embedded in. The radiation from the rest of the universe is literally warming it up, which is backwards from everything you'd expect. Space is warming the nebula the way a warm room warms a glass of ice water. And over time, the nebula will warm back up to match its surroundings. But for now, it's the coldest known thing in the natural universe. Now let's talk about the Kelvin scale a bit more, because there's something hiding in it that most people miss. We said 0 Kelvin is absolute zero. 2.7 Kelvin is the cosmic background. But when we start talking about hot things in space, the numbers climb in ways that are hard to hold in your head. The surface of our sun is about 5,778 Kelvin. But the corona, the outer atmosphere of the sun, the hazy crown you can see during a solar eclipse, is somewhere between 1 million and 3 million Kelvin. That's not a misprint. The atmosphere of the sun is hundreds of times hotter than its surface, and nobody fully understands why. This is one of the oldest unsolved problems in solar physics. You'd expect the temperature to drop as you move away from the hot surface. That's how every other heat source in your experience works. Move away from the fire, it gets cooler. But the sun does the opposite. The photosphere, the visible surface we see, sits at just under 6,000 Kelvin. And then as you move outward into the corona, the temperature climbs to millions of degrees. Some regions of the corona have been measured at 10 million Kelvin. It's like walking away from a campfire and feeling it get hotter the farther you go. Physicists have several theories about why this happens. The leading ones involve waves of energy moving through the sun's magnetic field, heating the corona the way a microwave heats food by agitating particles directly. But we don't have a clean, complete answer. The star we've been circling for billions of years still has this secret. So let's put this in perspective. The range of temperatures we encounter just in our own solar system runs from about 1 Kelvin if you could somehow find a shaded region far from the sun, all the way to tens of millions of Kelvin in the sun's corona. That's a range almost as wide as it's physically possible to imagine. And within that range we live in what you might call a narrow band of survivability, so thin that it's humbling. Human beings are comfortable between about 293 and 303 Kelvin. That's a window of maybe 10 degrees out of a range spanning tens of millions. We exist in an almost impossibly narrow slice of the possible. Now let's talk about what cold actually does to matter, because this is where the physics gets deeply strange. Most people know that cold makes things contract. The molecules in a cold object vibrate less, so they pack closer together. Steel bridges and train rails have expansion gaps built into them specifically because the metal will contract in winter and expand in summer. That's standard physics, nothing surprising there. But as you drop towards much colder temperatures, something else begins to happen. Something that breaks the normal rules. At extremely low temperatures, certain materials become superconductors. Electricity normally flows through a wire by hopping from atom to atom, and at each hop it loses a tiny bit of energy to resistance. That energy becomes heat. That's why your laptop charger gets warm. But at very low temperatures, some materials enter a state where their electrons pair up in a quantum mechanical dance and flow through the material with literally zero resistance. Not almost zero, exactly zero. A current set flowing in a superconducting loop will continue flowing forever, without any power source, without ever losing any energy. The current in a superconducting loop theoretically outlasts the stars. As long as the loop stays cold, the current never stops. The temperature at which most conventional superconductors kick in is somewhere around 4 Kelvin. That's the temperature of liquid helium. And that 4 Kelvin threshold is one of the reasons space itself is such an attractive environment for certain types of sensitive instruments. In deep space, far from any heat source, the background temperature is close enough to the superconducting threshold that some instruments can operate in near ideal conditions without a complicated active cooling system. The James Webb Space Telescope, which launched in December and reached its observing position about 1 million miles from Earth in early 2022, uses the cold of deep space as a passive refrigerator. Its infrared detectors need to be kept at around 6 to 7 Kelvin to function. It achieves this partly by sitting in the shadow of a 5-layer sunshield the size of a tennis court. The sunshield blocks sunlight and lets the telescope's instruments radiate their heat away into the 2.7 Kelvin background. Space's cold isn't just dangerous, sometimes it's a tool. But we should also talk about what happens to the human body specifically, because that's where this gets very immediate. Forget the spacesuit for a moment. Let's talk about what exposure to near vacuum conditions actually does to human tissue. Cold, in the sense of heat loss, would eventually be a problem. But in the immediate term, the bigger threat is pressure. At 0 atmospheric pressure, the water in your bodily fluids would begin to boil at body temperature. This is called ebullition. The boiling point of a liquid depends on pressure. Water boils at 100 degrees Celsius at sea level because that's where atmospheric pressure is high enough to require that much energy. Reduce the pressure to near zero and water boils at a temperature close to 37 degrees Celsius, which is roughly your normal body temperature. So in a vacuum, the moisture in your mouth, in your airways, in the fluid around your joints would all begin to vaporize. You'd swell. Your skin and soft tissues would expand with gas. This wouldn't kill you instantly, but it would incapacitate you within about 15 seconds as the oxygen-deprived blood stopped reaching your brain. You'd lose consciousness before you froze. The cold itself, as we said, would set in gradually. Without air to conduct heat away, your body loses heat primarily through radiation. At rest in shadow, a human body in a vacuum loses heat at roughly the same rate as a warm object losing heat by infrared radiation in a cold room. It takes time. Studies done on pressurization incidents and accidental vacuum exposures suggest that most of the immediate life-threatening damage comes from decompression rather than temperature. The freezing would come later. Cold is the universe's slow threat. Pressure is the immediate one. Now let's go somewhere more extreme. Let's go to the coldest places in the universe. We mentioned the Boomerang Nebula at 1 Kelvin. But in physics laboratories on Earth, we've created temperatures that are almost beyond comprehension in their closeness to absolute zero. In 1995, physicists at the University of Colorado created something called a Bose-Einstein condensate, a state of matter predicted by Einstein and Indian physicist Satyendra Nath Bose in the 1920s, but never observed until that year. The temperature required to create this state is around 100 to 200 nanokelvin. That's 100 to 200 billionths of a Kelvin. To put that in physical terms, that's closer to absolute zero than the Boomerang Nebula is to the background temperature of space. That's a temperature so low that the atoms involved essentially lose their individual identities and merge into a single quantum entity, a collective that behaves as one object. Thousands of atoms, all acting as one. At these temperatures, the normal rules of physics bend. The atoms aren't bouncing off each other anymore. They're not vibrating. They're barely doing anything. But quantum effects that are normally hidden, smeared out by the noise of all the jiggling, become visible. Atoms in a Bose-Einstein condensate can pass through each other. A fluid made from them has zero viscosity and flows without any friction at all. It's called a superfluid. If you stirred a cup of superfluid liquid helium and left it, it would keep swirling forever, or until the liquid warmed up enough to leave the superfluid state. No friction, no slowing down. The cold peeled back the ordinary behavior of matter and revealed the quantum layer underneath. This is one of the deepest things cold teaches us. At normal temperatures, the quantum nature of matter is hidden. The atoms are bouncing around so energetically that their quantum behaviors average out into the classical world we experience. Rocks behave like rocks, water behaves like water, but cool things down far enough and the quantum world starts showing through. The sharp lines between particles blur. Waves and particles start blending. The universe at its deepest level isn't made of billiard balls. It's made of something more like music, and cold lets you hear it. Let's step back from the lab and go back out into space. Because there's another extreme of cold we haven't talked about yet. And it's hiding in some of the most dramatic objects in the sky. When a massive star, one much bigger than our sun, reaches the end of its life, it collapses. The core implodes in a fraction of a second, and the outer layers are blasted away in a supernova, an explosion so bright that a single dying star can briefly outshine its entire galaxy of 200 billion other stars. The collapsed core left behind, if the star was massive enough, becomes a neutron star. A neutron star is what you get when gravity is so intense that it crushes electrons and protons together, forcing them to merge into neutrons. The result is an object made almost entirely of neutrons, packed together as tightly as the nucleus of an atom, about 12 to 15 kilometers across. That's roughly the distance across a medium-sized city, and it contains about 1.5 times the mass of our Sun. Now here's where temperature comes in. Just after it forms, a neutron star is hot beyond ordinary description. Its interior temperature is somewhere around 100 billion Kelvin. That's 100 billion Kelvin. The surface cools somewhat, down to around 1 million Kelvin, which is still 175 times hotter than the surface of our Sun. But neutron stars cool. Slowly, over millions and billions of years, they radiate away their heat. Old neutron stars can drop to surface temperatures of 100,000 Kelvin or below. And the interior, shielded by the dense outer crust, cools even further. Some older neutron stars may have interior temperatures approaching just a few 100,000 Kelvin, which is still extraordinarily hot by any human scale, but for a dead stellar remnant, it represents a dramatic cooling over cosmic time. But here's the really strange part. There's reason to believe that the interior of a very old neutron star might cross a threshold and become a superfluid. The neutrons in the core might, at sufficiently low temperatures, enter a quantum pairing state similar to what happens in superconductors. A superfluid neutron star interior. An object 12 miles across, containing more mass than the Sun in a quantum superfluid state. And we have evidence for this. When neutron stars are observed suddenly spinning faster, a phenomenon called a glitch, the leading explanation involves vortices of superfluid flowing through the star's crust. The quantum effects that we see in a laboratory at billionths of a Kelvin are also playing out, on a completely different scale, in the dense remnants of dead stars, the same physics, operating at wildly different scales. This is one of the things about physics that never stops being worth noticing. Now let's talk about something that doesn't show up in most conversations about space temperature. And it's a topic that matters because it tells us something about the deep future of the universe. We need to talk about where all the cold is going. The universe is expanding. You've probably heard this. Edwin Hubble demonstrated it in the 1920s by measuring the redshift of distant galaxies. Every galaxy is moving away from every other galaxy, not because they're flying through space, but because space itself is growing. The way dots drawn on a balloon move apart as you inflate it, but no single dot is the center. Every dot moves away from every other. And as the universe expands, the radiation inside it stretches. That cosmic background radiation we talked about, the ancient light from 380,000 years after the beginning, it's been stretching this whole time. When it was first emitted, it corresponded to a temperature of about 3,000 Kelvin. Today, stretched across 13.8 billion years of expansion, it corresponds to 2.7 Kelvin. It is cooling, and it will keep cooling. In the far future, if the universe keeps expanding, as it appears to be doing, and in fact accelerating due to the mysterious pressure we call dark energy, the background temperature will continue to drop. In about 1 trillion years, far longer than the current age of the universe, the background temperature will drop to around 0.3 Kelvin. In 10 trillion years, 0.03 Kelvin. The universe is on a very long road toward absolute cold, and this path has a name. Physicists call it the heat death of the universe, which is, confusingly, a death by cold. The term comes from thermodynamics. The second law of thermodynamics says that in any closed system entropy, the degree of disorder always increases. Heat always flows from hot to cold until everything reaches the same temperature. A cup of hot coffee in a cool room will eventually reach room temperature. Heat death means the universe will eventually reach a state where everything is at the same temperature, a temperature just barely above absolute zero, where no heat flows anywhere because there's nowhere colder for it to flow to. No temperature difference means no usable energy. No usable energy means no processes. No processes means nothing happens. Everything simply exists in a final undifferentiated cold, not an explosion, not a collapse, just a slow, quiet equalization into stillness. And it won't happen anytime soon. The Sun has about 5 billion years of hydrogen left. After that, it swells into a red giant, expands outward past Venus and possibly past Earth, then collapses into a white dwarf the size of our planet. White dwarfs cool over trillions of years into black dwarfs, dark cinders floating in the increasing cold. The stars themselves will eventually run out of fuel. In roughly 100 trillion years, the last star will finish burning. After that, the universe becomes a cold, dark place of black holes, neutron stars, and scattered black dwarfs. Then the black holes themselves evaporate through a quantum process Stephen Hawking described in 1974. A black hole radiates energy very slowly due to quantum fluctuations at its event horizon. The process is called Hawking radiation. The time it takes for even a stellar mass black hole to evaporate this way is around 10 to the 67th power years. Writing that out as a number, it's a 1 followed by 67 zeros. The entire current age of the universe, 13.8 billion years, is 13.8 followed by 9 zeros. Hawking, evaporation happens on a timescale that makes the current age of the universe look like the first blink of an eye. But eventually, even the black holes are gone. And then, an almost perfectly dark, almost perfectly cold, almost perfectly empty universe. A temperature infinitesimally close to absolute zero. A universe of maximum entropy, where nothing can happen because nothing has anywhere colder to go. That's the long ending, not fire, cold. But let's come back to the present, and let's get more specific about the texture of temperature in the universe as it is right now. Because it's not a uniform thing. The cold of space isn't even. It has geography. The very hottest places in the universe are in the cores of the most massive stars. The core of our Sun sits at about 15 million Kelvin. That's where nuclear fusion happens. Hydrogen atoms, moving fast enough, fuse together into helium and release energy. That energy is what eventually reaches you as sunlight. But more massive stars run hotter. A star around 10 times the mass of our Sun has a core temperature of around 70 million Kelvin. The most massive stars known, things like Eta Carinae, which contains somewhere between 100 and 150 solar masses crammed into a single stellar body, may have core temperatures exceeding hundreds of millions of Kelvin. And at the centers of galaxies, at the hearts of quasars and active galactic nuclei, you find accretion disks around supermassive black holes where temperatures in the innermost regions reach trillions of Kelvin. We're talking about regions where matter spiraling into a black hole is heated so intensely that it glows brighter than an entire galaxy of stars. So the universe spans from 1 Kelvin in the Boomerang Nebula to trillions of Kelvin at the edge of a black hole's event horizon. That range is not easily comparable to anything in human experience. The hottest temperature ever achieved in a physics experiment was in the Large Hadron Collider in 2012, when lead ions were smashed together and briefly created a temperature of around 5.5 trillion Kelvin. 5.5 times 10 to the 12th power Kelvin. That's hotter than the early universe a millionth of a second after the Big Bang. For a brief fraction of a second, inside a tunnel under the border between France and Switzerland, we recreated a condition that hadn't existed in the universe since 1 microsecond after everything began. And then it vanished. The fireball lasted less than a trillionth of a second. Now let's talk about something more subtle. Something that most people in the science communication space don't spend much time on because it requires holding 2 ideas at once. We've been talking about temperature as if it's a single number. Hot here, cold there. But in practice, measuring the temperature of something in space is genuinely complicated. And the complications reveal something important. When you measure the temperature of a gas cloud in space, what you're measuring is the kinetic energy of the particles in it. A very thin, very sparse gas cloud in space might have individual particles moving at speeds corresponding to temperatures of thousands of Kelvin. But the cloud is so thin, so many orders of magnitude less dense than even the best vacuum we can create in a lab, that if you put a thermometer in it, the thermometer would actually cool down. There's almost nothing there to transfer heat to it. The particles are moving fast, which corresponds to a high temperature, but there are so few of them that almost no energy actually gets exchanged. The formal temperature and the practical experience of temperature come completely apart. This is why astronomers distinguish between what they call the kinetic temperature of a gas, the speed of its particles, and its thermal equilibrium with its environment. The diffuse gas between stars in our galaxy, called the interstellar medium, can have kinetic temperatures in the thousands to tens of thousands of Kelvin. But it's so sparse, roughly 1 atom per cubic centimetre on average, that even though those atoms are moving fast, there are almost none of them. An astronaut floating in it would actually cool down, because so few particles would hit them. The formal temperature is high. The actual thermal effect is negligible. To put that density in perspective, right now, the air you're breathing contains about 20 billion molecules per cubic centimetre, 20 times 10 to the 18th. The interstellar medium has 1 atom per cubic centimetre. If you took a cubic centimetre of the interstellar medium, a space about the size of your thumbnail, and somehow gathered up every particle in it, you'd have a single hydrogen atom. That's it, 1 atom. And yet formally astronomers might say that region has a temperature of 8,000 Kelvin. The word temperature is doing something very different from what it does when you say the temperature outside is 8 degrees. Let's now go out to truly empty space. We've talked about the interstellar medium, the gas between stars within a galaxy. But between galaxies is something even emptier, the intergalactic medium. This is the space between galaxy clusters, and it is the closest thing the universe has to a true vacuum. The density here is less than 1 particle per cubic meter. 1 particle per cubic meter. To compare that to the air in your room, air at sea level contains about 2.7 times 10 to the 25th molecules per cubic meter. That's a 25-digit number. The intergalactic medium has 1 particle per cubic meter. These are different by a factor larger than any comparison from everyday experience can hold. The deepest, most perfect human-made vacuum we can create in a laboratory still contains millions of particles per cubic meter. The intergalactic medium is more empty than that. It approaches the closest thing to nothing that the universe offers. And in those spaces, the temperature of the radiation field is 2.7 Kelvin, almost nothing, almost perfectly cold. And yet, even here, the universe isn't perfectly still. Even in the deepest intergalactic void, the cosmic background radiation pulses through. Photons, one after another, crossing unimaginable distances, passing through emptiness that hasn't been disturbed in billions of years. The universe never quite achieves perfect silence. Now let's go a different direction. Let's talk about Mars and the Moon, because these are real places that real humans may actually visit in the coming decades, and their temperatures reveal something important about how radiation drives everything in the absence of atmosphere. The Moon has almost no atmosphere. What little gas it has is so tenuous, it barely counts. And because it has no atmosphere to distribute heat, its surface temperature swings from about 127 degrees Celsius during the lunar day to about negative 173 degrees Celsius during the lunar night. That's a swing of 300 degrees in the span of 2 weeks, because the lunar day and night each last about 14 Earth days. That's roughly the same as the difference between the coldest temperature ever recorded in Antarctica and the temperature required to sterilize surgical instruments in an autoclave in the same place, just 2 weeks apart. In permanently shadowed craters near the Moon's poles, where sunlight never reaches, the temperature drops further. Measurements from the Lunar Reconnaissance Orbiter found temperatures as low as negative 247 degrees Celsius in some shadowed craters. That's 26 Kelvin, cold enough to trap ice for billions of years. And indeed, water ice does exist in those craters, preserved since comets and asteroids deposited it long ago. The Moon carries cold libraries of ice in its permanent shadows, waiting untouched for billions of years. Mars is different. Mars has an atmosphere, but it's thin, only about 1% as dense as Earth's. And that thin atmosphere, made mostly of carbon dioxide, provides a little insulation, but not much. Average surface temperatures on Mars run around negative 60 degrees Celsius. Roughly the temperature in the upper atmosphere directly above Antarctica in winter. But the poles of Mars can get down to negative 125 degrees Celsius in winter, cold enough to freeze carbon dioxide directly out of the atmosphere. The polar ice caps you can see on Mars from Earth are partly water ice and partly frozen carbon dioxide, what we'd call dry ice on Earth. In winter, the poles get so cold that a significant fraction of the Martian atmosphere literally freezes onto the ground. The atmospheric pressure drops measurably, and in spring it sublimes back. Mars breathes in carbon dioxide. Mars exhales carbon dioxide. The whole atmosphere participates in a seasonal freeze-thaw cycle driven entirely by temperature. On Earth, we take it for granted that our atmosphere is stable. It doesn't freeze in winter. Our nitrogen and oxygen stay gaseous because Earth's orbit keeps us warm enough. Mars is just barely past the edge of that stability. Tilt it differently, move it slightly farther from the sun, or just have slightly less atmospheric carbon dioxide, and you get a planet where the air itself freezes in winter. The cold of space reaches right down to the planetary surface and starts claiming the atmosphere. Let's go back and think about what temperature means for life. Because this is where the cold of space becomes not just a physics question, but a deeply human one. Life on Earth operates within an extraordinarily narrow temperature range. Most biological processes that we rely on, the enzymatic reactions that drive metabolism, the folding of proteins that gives them their function, the fluidity of cell membranes that allows molecules to move in and out of cells, these all require temperatures between roughly 0 and 100 degrees Celsius. At 0 degrees, water freezes and the chemistry of life essentially stops. At 100 degrees, proteins denature, which means their carefully folded three-dimensional structures unravel like a strand of DNA being unspooled, and they stop working. Life as we know it is a narrow window of liquid water chemistry. And yet, life on Earth has pushed into the cold corners harder than you might expect. Tardigrades, those microscopic animals that look like tiny eight-legged bears and are probably the most resilient organisms we know of, can enter a state called cryptobiosis when conditions get extreme. They expel almost all the water from their bodies and essentially halt their metabolism. In this state, they've survived temperatures as low as -272 degrees Celsius, just 1 degree above absolute zero, and emerged alive when warmed up again. They can survive a vacuum. They've even survived low-level exposure to the radiation of open space in a 2008 experiment where tardigrades were taken outside a spacecraft in orbit. Not all of them made it, but some did. Some returned alive from the conditions of open space. There are bacteria that have been found in the deep cold of Antarctic ice, living at -20 degrees Celsius in the super cold brine channels between ice crystals. Lichen grow on rocks in the Antarctic interior, surviving average annual temperatures around -25 degrees Celsius, temperatures that would kill almost any other multicellular organism. Life is not fragile. Life finds every edge and lives on it. But even the hardiest life we know of uses chemistry that requires temperature to sit somewhere in a range that space, in its open depths, completely violates. Which raises the question: if there is life elsewhere in the universe, and the physics of chemistry and biology strongly suggests that life of some form is possible in many places, then temperature is going to be one of the central constraints shaping what that life looks like. Cold slows chemistry down. An organism living in a very cold environment, somewhere like the ice moons of Jupiter, Europa or Ganymede, or the ice moons of Saturn, Enceladus or Titan, would need to either operate with extremely slow chemistry or find ways to stay warmer than their environment. The oceans under Europa's ice shell may be only slightly above 0 degrees Celsius, warmed by tidal flexing from Jupiter's gravity. If life exists there, it lives in water that is perhaps a few degrees above freezing, under an ice shell miles thick in permanent darkness, around chemical gradients from hydrothermal vents on the seafloor. And here's the thing: we have environments exactly like that on Earth. And they're full of life. Let's come back to Earth's surface and think about how we actually experience cold in a way that connects to everything we've been talking about. Because there's a physics lesson hiding in the ordinary experience of feeling cold. When you feel cold, what's happening is heat is leaving your body faster than your metabolism can replace it. Your skin temperature, especially on exposed areas like your face and hands, drops because heat is conducting away into the air and radiating away into the environment. Wind makes this much worse because it constantly replaces the thin layer of warm air that builds up against your skin with fresh, cold air. This is what wind chill is. It's not that the temperature is lower, it's that heat is leaving your body faster. On a still day at -10 degrees Celsius, the heat loss rate is equivalent to still air at -10. On a windy day with the same temperature but strong gusts, the rate of heat loss from exposed skin matches what would happen at -30 or colder. Your body experiences the cold faster, but the actual air temperature hasn't changed. In space, there's no wind, so the wind chill effect doesn't exist. But there's also no air at all. So while you won't be losing heat by conduction or convection, you will be losing it by radiation. If you're in shadow, the radiation loss is slow but relentless. If you're in sunlight, you're absorbing radiation at the same time, and the balance depends on your surface properties. Dark surfaces absorb and radiate more. Light surfaces reflect and radiate less. This is why spacewalking astronauts wear white suits. The white reflects most of the solar radiation, preventing overheating. And their suits have active cooling systems inside, circulating cool water through a network of tubes in the garment. The suit isn't keeping them warm, it's keeping them from overheating, while also insulating them during periods in shadow. Thermal management in space is a constant multi-directional engineering challenge. Now let's go somewhere we haven't been yet. Let's talk about what happens to the temperature of space in the context of cosmic structures. Because the universe has structure, and that structure has thermal properties. Galaxies like our Milky Way are embedded in dark matter halos. They're made of hundreds of billions of stars plus enormous amounts of gas and dust. The spiral arms of a galaxy are actually regions where the gas density is higher and star formation is more active. Inside the dense regions, near active star formation, temperatures in the gas can reach 10,000 to 100,000 Kelvin. Pushed and heated by radiation and stellar winds from hot young stars. But in the cooler, quieter molecular clouds, where stars haven't yet ignited, temperatures drop to around 10 to 30 Kelvin. Inside the densest parts of these clouds, the cores where protostars are just beginning to collapse, temperatures can be as low as 10 Kelvin, about 10 degrees above absolute zero. The nurseries where stars are born are some of the coldest places in our galaxy. Why are molecular clouds cold? Because gas clouds in space cool through radiation. The molecules in the cloud absorb energetic photons from nearby stars and emit lower energy infrared photons. They're radiating away energy all the time. If the cloud is dense enough and shielded enough from hot stars, it can radiate itself down to very low temperatures. And as it cools, it contracts. As it contracts, it gets denser. As it gets denser, small regions within it can reach densities where gravity starts pulling things together. A gravitational collapse begins. The cloud fragment gets smaller and denser and hotter as gravitational potential energy converts to heat. Eventually, if the fragment is massive enough, it gets hot enough in the center for nuclear fusion to begin. A star is born, out of the cold of a molecular cloud. Every star we see in the sky began as a whisper of cold gas, dense enough and cold enough to to fall together. There is something almost paradoxical in that. The cold of space is what makes stars possible. If the gas in molecular clouds didn't cool, it wouldn't contract. It wouldn't collapse. There would be no stars, no solar systems, no planets, no sunlight, no life. The cold of space is not just a backdrop. It is an active ingredient in the formation of the universe's structure. Let's now go up in scale to galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe. They can contain hundreds or thousands of individual galaxies, each with hundreds of billions of stars all bound together by gravity and embedded in enormous halos of dark matter. And between the galaxies, filling the space within the cluster, is a thin, hot gas called the intracluster medium. This gas is genuinely hot, not just warm. Hot in the way physicists mean when they say something has a temperature of 10 million to 100 million Kelvin. This gas is so hot that it emits X-rays, not visible light, X-rays. The clusters of galaxies in our universe glow in X-ray light because of the extremely hot gas between their constituent galaxies. How did this gas get so hot? Gravity. As matter fell together to form the cluster over billions of years, gravitational potential energy converted to kinetic energy and then to heat. The gas was shock heated as it fell into the cluster's gravitational well. And once trapped, it radiates this heat away slowly, cooling over billions of years. In some clusters, this cooling is fast enough that the gas in the center actually condenses and falls inward, and new stars form out of it. We call these cooling flows, though the actual physics turns out to be complicated by energy input from the central supermassive black hole. So we have, in the universe, a giant spread of temperatures. Molecular clouds at 10 Kelvin giving birth to stars. Stars burning at millions of Kelvin in their cores. Dead stellar remnants cooling over billions of years. Galaxy clusters glowing in X-ray light at tens of millions of Kelvin. And underlying everything, the 2.7 Kelvin cosmic background, the hum of the beginning, the oldest light in the universe, threading through every cubic centimetre of space between every structure. The universe is not a simple thing. It is a thermal landscape of staggering range and complexity, and we live inside it. Let's talk about something even more immediate now. Let's talk about the first time humans truly understood what space cold meant. The Mercury program in the early 1960s was the first time Americans sent humans to space. The astronauts wore suits derived from high-altitude jet fighter suits. Thermal management wasn't fully understood. The capsules got hot. The astronauts sweated. Some capsule instruments overheated. By the time of Apollo, engineers had developed much more sophisticated thermal control systems. The Apollo spacecraft used a technique called passive thermal control, informally called the barbecue roll. The spacecraft was slowly rotated, about one rotation every 20 minutes, to distribute the heat load evenly across all sides. Without this roll, the sun-facing side would have baked, while the shadow side froze. The barbecue roll kept the whole vehicle in a thermal equilibrium that the hardware could handle. The Apollo spacesuits themselves were multi-layered thermal management devices. The outer layer was a white, highly reflective material to reduce solar heat absorption. Inside were layers of insulation. Against the skin, a water-cooled garment, a network of flexible tubes through which cold water circulated, directly carrying body heat away. And all of this was necessary because in the vacuum of space, your body's normal heat loss mechanisms fail completely. The sweat on your skin doesn't evaporate the way it does in air. The air in the suit heats up. Without the cooling system, Even in the vacuum of space, an astronaut in a sealed suit doing physical work would overheat. The challenge of space isn't just surviving the cold, it's managing the heat your own body generates. On the lunar surface, the suits operated in conditions unlike anywhere on Earth. The suit's feet would be standing on ground that was either baking in sunlight at 127 degrees or dropping toward negative 173 in shadow. The astronauts had to move quickly enough to keep themselves warm during shadow periods, but not overheat in sunlight. And the dust. The lunar dust was a thermal nightmare. It was fine enough to coat everything, and fine dust particles have different thermal properties than solid rock. It was very good at absorbing solar radiation and heating up quickly. If dust got on the suit, it changed the thermal behavior. On the last few Apollo missions, the astronauts noted that after working on the surface, their suits were so coated with dark dust that the reflectivity was significantly changed. The suits were getting warmer. Now let's jump to a different topic that's related but less obvious: the temperature of the sun's light. When sunlight reaches Earth, the temperature of the light, meaning the temperature of the black body radiation it corresponds to, is about 5,778 Kelvin. That's the temperature of the solar surface from which it was emitted. By the time it reaches Earth, it has spread out, diluted across the growing sphere of distance, but its colour, its spectral distribution, still tells you something about the source. The colour of a light source tells you its temperature. Hot things glow blue-white, cooler things glow red. Our sun, at around 5,778 Kelvin, glows yellowish-white. You can actually see this gradation in the night sky. The red stars are the cooler ones, the blue-white stars are the hot ones. Betelgeuse, the red star at the shoulder of Orion, has a surface temperature around 3,500 Kelvin. Rigel, the blue-white star at Orion's foot, burns at about 12,000 Kelvin. Every star in the sky is broadcasting its temperature in the form of its colour. The night sky is a temperature map. This relationship between colour and temperature is described by a piece of physics called Wien's displacement law. It says that the peak wavelength of radiation emitted by a black body is inversely proportional to its temperature. Hot things emit shorter wavelengths, which means bluer light. Cooler things emit longer wavelengths, which means redder light. And very cool things, things at room temperature, emit their radiation in the infrared, completely invisible to the human eye. But you feel it. Everything around you, every piece of furniture, every wall, every other person in the room is radiating infrared radiation right now based on its temperature. Your skin detects this as warmth when you stand near a warm object. The heat you feel from a fireplace several feet away is entirely infrared radiation, the same mechanism that the sun uses to warm the Earth, and the same mechanism that slowly bleeds heat from a human body into the cold of space. The cosmic background radiation at 2.7 Kelvin emits its peak radiation in the microwave part of the spectrum. Wien's law says that for a black body at 2.7 Kelvin, the peak wavelength is about 1.9 millimeters. That's in the microwave range, slightly shorter than microwave radiation in your kitchen oven. The universe hums at a wavelength just slightly shorter than the waves in your microwave. And this radiation is completely uniform in all directions. Wherever you point a sensitive microwave detector in the sky, above all the ordinary sources, you find this background hum. It comes from 360 degrees of sky with a uniformity that is almost perfect. Almost, but not quite. And the tiny deviations, variations, at the level of about 1 part in 100,000 map the slight density differences in the early universe that eventually grew into the galaxies and galaxy clusters we see today. The texture of the cosmic background radiation is the shadow of the seeds of all structure. The WMAP satellite measured these variations in extraordinary detail in the early 2000s. The Planck satellite followed in the 2010s with even sharper measurements. From these maps, cosmologists extracted the most precise values we have for the basic parameters of the universe. Its age, its composition, the proportions of ordinary matter, dark matter, and dark energy. All of it encoded in the temperature variations of a field of radiation at 2.7 Kelvin. Some of the most important information we have about the universe as a whole is hidden in patterns at the billionths of a degree level in a background radiation field that we can't even feel. Let's slow down and let that sit. The universe is telling us about its beginning in radiation, so cold, so faint that it doesn't warm your skin. The entire story of the first 380,000 years is written in a cosmic whisper that arrives from every direction, day and night, passing through walls, passing through us, carrying information 13.8 billion years old. We built instruments sensitive enough to read it, and what we found was the universe's baby picture. Now let's turn to something more immediate and more local. Let's talk about what the cold of space means for satellites and spacecraft we've already sent out there. The Voyager probes. Voyager 1 and Voyager 2 were launched in 1977, designed for 5-year missions to Jupiter and Saturn. Voyager 1 is now about 23 billion kilometers from the Sun, which is roughly 155 times the distance from the Earth to the Sun, or about 156 AU. An AU being the Earth-Sun distance. At that distance, sunlight is about 24,000 times weaker than it is here. The temperature environment out there far in the outer reaches of what we call the heliosphere involves temperatures in the surrounding medium that are very different from anything close to home. The heliosphere is the bubble of solar wind and solar magnetic field that surrounds our solar system. The boundary of the heliosphere, called the heliopause, is where the solar wind's pressure drops enough for the interstellar medium to push back. Voyager 1 crossed the heliopause in August 2012. It is now in interstellar space. And the temperature measurements from Voyager confirm something important. Just inside the heliopause is a region called the heliosheath, where the solar wind slows and compresses. The temperature there was measured at around 50,000 Kelvin. But outside the heliopause, in the true interstellar medium, the kinetic temperature of the sparse particles drops. Meanwhile, the spacecraft itself cools. Its nuclear power source, a set of plutonium-238 heat sources, has been slowly declining. When Voyager 1 was launched, its power source generated about 470 watts, comparable to a few incandescent light bulbs. Today, about 48 years later, it generates less than half that. It's using the heat to keep its instruments above a minimum operating temperature. One by one, instruments have been shut down to conserve power. Eventually, probably in the next few years, the power will be too low to maintain the spacecraft's temperature, and it will fall silent. An object sent into interstellar space will, over millions of years, cool toward the background temperature of 2.7 Kelvin. Its metal components will contract. Some materials will become brittle and crack. Certain chemical bonds in polymer components will break. Without any heat source, without any medium to exchange heat with, it simply radiates away whatever thermal energy it had, slowly, toward the cosmic floor. The spacecraft we've sent out are temporary. not in the sense of years or centuries, but on cosmic timescales. A cold metal object radiating away its heat will eventually reach equilibrium with the universe itself. Let's go back now to something we should unpack more carefully, because we've been throwing around temperatures in the millions and billions of Kelvin, and we haven't really stopped to make them feel real. Let's do that. A temperature of 1 million Kelvin corresponds to particles moving at an average speed of about 4,000 kilometers per second. That's more than 1% of the speed of light. To put that in terms you can feel in your bones, the fastest thing ever launched by humans was the Parker Solar Probe, which reached a speed of about 690,000 kilometers per hour, roughly 0.064% of the speed of light. The average particle in a million Kelvin plasma is moving about 15 times faster than the fastest spacecraft ever built. Not a few percent faster, 15 times faster. Heat at stellar interior temperatures is not a metaphor. It is kinetic energy at a scale that puts our engineering achievements in perspective. At a temperature of 1 billion Kelvin, particles are moving at speeds approaching several percent of the speed of light. This is the kind of temperature found in the cores of supernovae during the explosion. For a few seconds during a supernova, the core reaches temperatures around 10 to 100 billion Kelvin. And at those temperatures, photons carry enough energy to spontaneously create matter. High-energy photons can collide and produce electron-positron pairs. Matter literally forms from energy because the temperature is high enough. Einstein's equation, E equals mc squared, runs backwards. Energy becomes mass. The extreme heat of a supernova is so intense that it temporarily violates the normal direction of nuclear physics. Normally, matter releases energy. In a supernova core, energy creates matter. And at the very beginning, in the first fractions of a second after the universe began, temperatures exceeded 10 to the 32nd Kelvin. That's a 10 followed by 32 zeros. At those temperatures, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified. They weren't separate things. They were one force. The universe has been cooling and separating ever since. As the temperature dropped, the forces crystallized out from each other like different compounds precipitating from a cooling solution. The cold progression of the universe's expansion is the story of how the four forces became distinct. The universe cooled and the world became complicated. We think of cold as simple and emptiness. But this cooling process is what created complexity. It's what created atoms. It's what created molecules. It's what created the chemistry that makes life possible. A universe that stayed at 1 billion Kelvin would have no atoms, no molecules, no planets, no life. The cooling of the universe wasn't the death of possibility. It was the birth of it. Let's come back to something very close to home. Let's come back to the sky you can see. Because there's a cold story right there that most people have never thought about. The sky looks dark at night. This seems obvious. The sun isn't up. Of course it's dark. But it's actually not obvious at all. If the universe were infinite and eternal and uniformly full of stars, then no matter which direction you looked, your line of sight would eventually intersect a star. The whole sky would be as bright as the surface of the sun. There would be no dark night. This puzzle is called Olbers' paradox, and the resolution involves the expansion of the universe and the finite age of the stars. Light from distant stars takes time to reach us, and the universe has only been around for 13.8 billion years. So light from stars more than 13.8 billion light years away hasn't reached us yet. It's on its way, but it hasn't arrived. The observable universe is finite. And even within the observable universe, the expansion of space has shifted light from the farthest sources far out of the visible range. The dark night sky is a product of the universe having a finite age and an expanding volume. You look at the dark patches between stars, and what you're looking at is the darkness of a young universe, still small enough that light from all its stars hasn't filled in the gaps. And embedded in that darkness, invisible to our eyes, is the cosmic background radiation. A faint microwave glow from the moment the universe became transparent. The dark night sky isn't empty. It's full of ancient light in wavelengths we can't see. This connection between the cold of the background radiation and the darkness of the night sky is one of those physics crossroads where several big ideas touch each other. The age of the universe, the expansion of space, the finite speed of light, and the temperature of the cosmic background all intersect in the simple fact that the sky is dark at night. Every night when you look up at the dark patches between the stars, you're looking at evidence for all of these things at once. Let's now spend some time talking about how cold affects specific materials and technologies in space, because this is practical and it reveals the engineering genius of the people who've worked in this field. Metals behave very differently at cryogenic temperatures. Most metals become more brittle as they get cold. Steel, for example, undergoes a ductile to brittle transition somewhere around -40 to -60 degrees Celsius. At room temperature, steel can absorb impacts by deforming. Below the transition temperature, it shatters like glass. This is why the Titanic's hull plates failed as catastrophically as they did. The water temperature of the North Atlantic that night was around -2 degrees Celsius, just barely above freezing. The steel of the era had a ductile to brittle transition that was not far below those temperatures, and when the hull hit the iceberg, instead of denting and deforming, it cracked. Cold changed the failure mode of the steel. The temperature of the ocean water was part of why the ship sank the way it did. In space, structural materials must be tested across the full range of temperatures they'll experience. The bolts that hold a spacecraft together, the hinges of its solar panels, the cables in its antenna, all of these go from roughly 120 degrees Celsius to -160 degrees Celsius in orbit multiple times a day. They must not crack, they must not seize, they must not lose their electrical conductivity. Choosing materials for spacecraft is partly a list of mechanical and electrical requirements, and partly a list of thermal requirements that eliminate most ordinary options. Some metals do better in the cold. Aluminum becomes stronger as it cools. Titanium also maintains its strength well at cryogenic temperatures. Some special alloys of steel are designed specifically to remain ductile at very low temperatures. These are called cryogenic steels, and they're used in liquefied natural gas storage tanks, which hold their cargo at about -162 degrees Celsius. The engineers who designed the first deep space probes were working without a complete playbook. They were learning by trial and cold what materials survived. The James Webb Space Telescope is the best current example of extreme cold engineering. Its primary mirror, 18 hexagonal segments of gold-coated beryllium, must operate at about -233 degrees Celsius, or 40 Kelvin. The gold coating is there because gold is excellent at reflecting infrared light. The mirror observes the universe in infrared, which is the red-shifted light from the most distant galaxies. But infrared detectors only work when they're cold. If the detector is warm, it emits its own infrared light, which drowns out the faint signals coming from across the universe. The telescope itself must be colder than the things it's looking for. So the sunshield cools most of the telescope passively, and the mid-infrared instrument has its own dedicated cryocooler that drops it to about 7 Kelvin. The cryocooler uses a refrigeration cycle, the same basic physics as your refrigerator at home, but designed to operate at extreme temperatures in a space environment. It uses helium gas compressed and expanded in a carefully timed cycle to pump heat from the cold detector up to a warmer radiator facing deep space. That radiator is one of the most important pieces of engineering on the telescope. It faces away from the sun, away from Earth, away from any warm source. It faces the cold of deep space directly, and it radiates heat away into that 2.7 Kelvin background. The telescope uses the cold of the universe itself as a heat sink. Like a hot cup of coffee placed in a cold room, the telescope's excess heat leaks away into the cold of space. Deliberately, by design. The cold of the universe is not just a hazard to be managed, it's a resource. Let's talk now about something that lives in the cold in a completely different way. Let's talk about dark matter. Dark matter makes up about 27% of the universe. Ordinary matter, the stuff you and I and every planet and star are made of, makes up only about 5%. The rest is dark energy. Dark matter doesn't emit light. It doesn't absorb light. It interacts with ordinary matter only through gravity. We know it's there because of its gravitational effects on galaxies and galaxy clusters. Galaxies rotate faster at their edges than they should if only the visible matter were present. The gravity of unseen dark matter halos holds them together. Now here's the temperature connection. The thermal properties of dark matter are unknown, but they affect what dark matter is. If dark matter particles were fast-moving, hot, when they decoupled from the rest of the universe in the early epochs, they would have erased small-scale structure. You wouldn't get small galaxies or small galaxy clusters. The universe would be made of large, smooth sheets. We call this hot, dark matter. The observations, however, show small galaxies forming early. The universe has plenty of small-scale structure. This tells us that dark matter was moving slowly when structures formed. Cold dark matter, moving slowly compared to light, cold in the physics sense. The structure of the universe, the web of filaments and clusters and voids, is a fingerprint of the fact that dark matter was cold. The largest map of cosmic structure tells us the temperature state of a particle we've never directly detected. And the leading candidates for what dark matter actually is are particles that would have been cold. WIMPs, weakly interacting massive particles, and axions, which are different kinds of hypothetical particles, would both qualify as cold dark matter. The search for these particles is one of the most active frontiers in physics. Deep underground laboratories, shielded from cosmic ray interference, contain tanks of ultra-pure liquid xenon or germanium crystals, cooled to cryogenic temperatures to reduce thermal noise, waiting for the rarest possible event, a dark matter particle colliding with an ordinary nucleus. The coldest detectors in the world, operating just above absolute zero, built to feel the universe's most invisible component. The cold is both the subject of the search and the tool being used to conduct it. Let's take a different angle now. Let's think about the cold of space from the perspective of a photon, a particle of light. A photon has no mass. It always travels at the speed of light, which is about 299,792 kilometers per second, roughly the distance from the Earth to the Moon every 1.3 seconds. A photon doesn't experience time. From its own reference frame, because it moves at the speed of light, time dilation compresses its journey to zero duration. The photon emitted from a distant star and absorbed by your retina has, from its own perspective, never spent any time travelling. It was emitted and absorbed in the same instant, which means, in a very specific sense, every photon you've ever seen from the night sky has been travelling for 0 seconds from its own perspective, even if from our perspective it took millions of years. Now, what does this have to do with temperature? A photon carries energy. Its energy is determined by its frequency. High-frequency photons like X-rays and gamma rays carry enormous energy. Low-frequency photons like radio waves and microwaves carry very little. The cosmic background radiation at 2.7 Kelvin is made of very low-energy microwave photons. Each one carries about 4 × 10⁻23 joules of energy. To put that in physical terms, to lift a single grain of sand 1 centimetre off a table requires about 1,000 times more energy than one of these photons carries. These photons are energy in its most diluted, most stretched out form. They are what energetic photons become after 13.8 billion years of travelling through an expanding universe. The energy of the Big Bang itself, distributed across 13.8 billion years of space and time, thinned to a whisper. And yet these photons still push things. They exert radiation pressure. It's tiny, tiny beyond ordinary description, but it's real. In the far future, when all the stars have gone out and the universe is dark, the photons of the cosmic background radiation will continue pushing on anything they encounter. A piece of floating metal in the deep future of the universe will be very slightly nudged by microwave photons for as long as they persist. The radiation pressure of the nearly dead universe pushing against the remnants of the matter era. Let's come back to the human scale again, because we need to connect all of this to us. To the fact that we're alive, on a planet, in a star system, in a galaxy, all of it floating in the cold. The Earth's surface sits at an average temperature of about 288 Kelvin. That's about 15 degrees Celsius. Without our atmosphere, the Earth's average temperature would be around 255 Kelvin, which is negative 18 degrees Celsius, well below freezing. Our atmosphere, specifically the greenhouse gases in it, carbon dioxide, water vapour, methane, trap infrared radiation, and raise the surface temperature by about 33 degrees. This greenhouse effect is not a recent human discovery. It's been operating for billions of years. It's the reason liquid water exists on Earth's surface. It's the reason life is possible. The thin shell of gas wrapped around our planet is the difference between a living world and a frozen rock. And this thin shell is what separates us from the cold we've been talking about all night. The atmosphere is about 100 kilometers thick, if you include all the trace gas above the dense lower layers. But 99% of the mass is in the lowest 32 kilometers, a layer that if you compressed it to sea level density would be about 8.5 kilometers thick. That 8.5 kilometers of gas is the thermal blanket that makes the surface temperature differ from the cold of space by nearly 270 degrees. The distance between the Earth we live on and the deep cold of space is less than 10 kilometers of atmosphere. Drive that far on a highway and it takes 7 minutes. But this blanket is not passive, it moves. Winds redistribute heat from the equator to the poles. Ocean currents carry heat between hemispheres. Weather systems are heat engines, converting the temperature difference between the warm tropics and the cold poles into kinetic energy of spinning air masses. Every thunderstorm, every hurricane, every blizzard is, at its core, the atmosphere trying to distribute heat more evenly. The atmosphere is working constantly to erase the temperature differences that sunlight creates. And the cold of space is always pulling from above, trying to drain the heat away. The weather you experience every day is the battlefield between a star and a void. Let's go now to something even more visceral. Let's talk about what happens to a human body at extreme cold on Earth, because it gives us a physical, felt sense of what cold does, even if the scales are different from space. Hypothermia begins when core body temperature drops below 35 degrees Celsius. Normal body temperature is 37 degrees. That's a drop of only 2 degrees. At this stage, you shiver intensely, your judgment starts to impair, and your body redirects blood away from your limbs toward your vital organs. Your fingers and toes get cold fast because your body is sacrificing the periphery to keep the core warm. At 32 degrees, shivering stops. When shivering stops, it's not because you're warmer, it's because your body's thermoregulation has essentially given up. At 28 degrees Celsius, the heart can develop arrhythmias. At 24 degrees, spontaneous cardiac arrest is likely. At 20 degrees, brain function has essentially stopped. People have been resuscitated after core temperatures as low as 13.7 degrees Celsius, in rare cases involving cold water immersion. The body's chemistry had slowed so much that the brain sustained less damage than it would have at normal temperature. The cold, in those extreme cases, paradoxically bought time. Cold has been used medically for exactly this reason. Therapeutic hypothermia, deliberately cooling a patient after cardiac arrest to around 32 to 34 degrees Celsius, can reduce brain damage because the cold slows the metabolic processes that cause harm during oxygen deprivation. Surgeons performing complex heart operations sometimes cool the patient's body to as low as 18 degrees Celsius, essentially stopping the heart, the circulation, and the brain for periods up to 30 minutes while they work. The patient's chemistry is running so slowly that tissues can survive without fresh oxygen supply. Then the body is re-warm, the heart restarted, and the patient wakes up. Cold, used carefully, is a tool that buys the impossible. Time without a heartbeat. Cryogenic preservation of biological tissue takes this further. When cells are cooled to cryogenic temperatures, usually in the presence of cryoprotectants that prevent ice crystal formation, their chemistry essentially stops. They can be stored indefinitely. Blood banks store red blood cells for up to 42 days in liquid form. Sperm and embryos can be stored for years or even decades in liquid nitrogen at negative 196 degrees Celsius. The biological clock stops, not metaphorically, literally. The chemistry that causes aging and death doesn't run at those temperatures. The stored cells are neither alive nor dead in the normal sense. They're in a paused state, waiting for warmth. Some researchers are exploring whether this could be extended to whole organs for transplant, to tissues, eventually perhaps to entire humans. The concept of human cryonics, freezing a person after death with a hope of future revival, exists. It's practiced by a small number of people. The scientific consensus is that current methods almost certainly destroy too much cellular structure for revival to be feasible. But the underlying principle that cold can pause biology at the molecular level is real. The gap between what we do now and what might theoretically be possible is a gap of technology. not of physics. What we're really brushing up against here is one of the deepest connections between temperature and time. All chemistry runs at a rate proportional to temperature. Cold slows every reaction. At absolute zero, chemistry would stop entirely. In a sense, the passage of biological time is a thermal phenomenon. You age because chemistry runs in your cells. Cool those cells enough and aging slows. The coldest places in the universe, the places where temperature approaches the quantum floor, are places where chemical time has nearly stopped. The Boomerang Nebula at 1 Kelvin is a place where chemistry runs glacially slowly. If life could somehow persist there, it would age at a rate that would make the cooling of a white dwarf star look sudden. This makes you wonder something. In a universe trending toward cold over trillions of years, is there a sense in which life's window is tied to the window of stellar warmth? Stars are thermal anomalies. They're pockets of extreme heat in a cooling universe powered by nuclear fusion, lasting for millions or billions of years before their fuel runs out and they go cold. Life requires energy flows, which require temperature differences. Stars provide those temperature differences. When the stars go out, the temperature differences available for biology will drop to the level of residual heat from white dwarfs, and eventually to nothing meaningful. Some physicists have speculated about whether life could persist in a cooling, dark post-stellar universe, not life as we know it, not carbon-based chemistry. But could some form of information processing, some kind of pattern that perpetuates itself and responds to its environment, survive on the tiny residual heat flows available in the far future? The answer is probably not. As the universe approaches heat death, the available temperature difference approaches zero. A heat engine needs a temperature difference to do work. At zero difference, the engine does no work. And without work, no information processing is possible. The universe's cooling is not just the cooling of matter. It is the gradual extinguishing of every process, including thought. But we're getting ahead of ourselves. That's trillions of years away. Right now, the universe is in the middle of its stellar era. Stars are forming and dying. Galaxies are colliding and merging. Planets are circling suns. Life, at least in one known place, has learned to look at the cold universe around it and ask why. Let's come back to the present and think about something very practical. What the cold of space means for current missions and technologies. One of the less discussed engineering challenges of sending humans to Mars is the thermal environment. We mentioned the average temperature of -60 degrees Celsius, but that's an average. Near the equator, temperatures can reach +20 degrees Celsius on a sunny summer afternoon. That's comfortable, shirt-sleeve weather. But a few hours later, the same spot on Mars is at -80 Celsius. The range isn't just large, it's large over short time periods, because Mars doesn't have much of a heat reservoir. Earth's oceans store enormous amounts of heat and smooth out temperature swings. Mars has no significant liquid reservoir. The temperature swings nakedly with the sun. Spacesuits for Mars need to handle a wider thermal range than Apollo suits. They need to deal with Martian dust, which behaves differently from lunar dust. They need internal life support that handles the thin carbon dioxide atmosphere. And critically, they need heating systems that work reliably for extended missions. If a heater fails on the Martian surface during night, temperatures will drop fast. The insulation in an unheated suit would not hold against a Martian night for more than a few hours. The cold of Mars is serious. Not space-level cold, not boomerang nebula cold, but deep enough that it kills you on a timescale of hours without active countermeasures. For instruments on Mars, temperature management is critical. The Perseverance rover, which landed on Mars in February 2021, uses both heaters and passive insulation to keep its instruments within operating range. The rover's body is a warm box. Heat generated by the electronics is trapped inside. Radioisotope heater units, small pellets of plutonium dioxide that generate heat from radioactive decay, warm critical components overnight. Each heater unit generates about 1 watt of thermal power. Small, but in the thermal budget of a rover on Mars overnight, that 1 watt keeps a battery or an instrument just above its minimum operating temperature. Small heaters quietly running all night, keeping the mission alive in the cold. The engineering of cold is everywhere in space exploration. The liquid hydrogen and liquid oxygen propellants in rockets must be stored at cryogenic temperatures. Liquid hydrogen boils at negative 253 degrees Celsius, just 20 degrees above absolute zero. This is warmer than the cosmic background, but colder than anything in normal human experience. Handling these propellants requires insulated tanks, venting systems for the inevitable slow boil-off, and careful management during the countdown. On a warm day, the liquid oxygen and hydrogen in a rocket's tanks are actively trying to boil. The tanks are constantly venting vapor. You can see this on rocket launches, the white vapor clouds billowing off the rocket as it sits on the pad. That's cryogenic propellant boiling off. The countdown clock isn't just waiting for systems to be ready. It's racing against the loss of propellant. Let's pause and think about something simpler. Something almost everyone has experienced. Because it connects back to everything. Have you ever looked up at the night sky on a truly clear night, far from city lights? Not just the suburban version, but the kind of sky you get in the mountains, or at sea, or in the desert, where the Milky Way is a solid river of light across the whole sky. If you have, you've seen the real sky. And that sky is a thermal document. Every point of light has a temperature. The colours tell you the temperatures. The redder ones are cooler, the bluer ones are hotter. The absolute black between them is not true emptiness, but a 2.7 Kelvin glow of ancient photons. The patches you can see as faint smudges, those are galaxies, hundreds of billions of stars each, so far away that the whole thing fits in the space of one apparent degree. And all of it, everything you can see and everything between what you see, is bathed in this radiation field at 2.7 Kelvin. The oldest persistent thing in the universe, not the stars, not the galaxies. The background radiation outlasts them. The stars will go dark, the galaxies will merge and fade. But the cosmic background radiation will persist, cooling, 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 for trillions of years, after the last star has gone out. The universe will be dark but not completely cold. For a very long time, longer than most numbers we use can properly represent, it will glow in the microwave. A ghost of its beginning. Now let's bring up something we haven't talked about yet. Something that changes the picture of the cold of space in an interesting way. We've been talking mostly about temperature in terms of particles and radiation. But there's another kind of energy in space that doesn't fit neatly into either category. Dark energy. Dark energy is what drives the accelerating expansion of the universe. It was discovered in 1998 when two independent teams of astronomers studying distant Type IR supernovae found that the universe isn't just expanding, it's speeding up. Galaxies are moving apart faster and faster. This acceleration is attributed to dark energy, a property of space itself that generates a kind of repulsive pressure. Dark energy makes up about 68% of the total energy content of the universe. Dark energy doesn't have a temperature in the conventional sense. It's not a gas. It's not a plasma. It's not made of particles. As far as we know, it's a property of the vacuum. The vacuum of space has energy. This is one of the predictions of quantum field theory that is actually well established, though the measured value of the vacuum energy doesn't match theoretical predictions particularly well. But the key point here is that dark energy has a constant energy density throughout space. As space expands and more volume exists, more dark energy exists. Its density stays the same even as the universe grows. This is what drives the acceleration. More space means more dark energy, means more repulsion, means faster expansion. And this accelerating expansion has a thermal consequence. As space expands faster and faster, distant regions of the universe are moving apart from us faster and faster. Eventually, regions that are receding faster than light, due to the expansion of space, rather than motion through space, will be causally disconnected from us. In the far future, in a dark energy-dominated universe, all the galaxies we can currently see, except for those in our local cluster, will eventually recede beyond our cosmic horizon. The sky will become dark. Our descendants, if any exist far enough in the future, will look up at a sky that contains only the local group of galaxies. They will have no way of knowing the universe beyond exists. The light from those distant galaxies, shifted to ever longer wavelengths by the accelerating expansion, will become undetectable. And the background temperature, already at 2.7 Kelvin, will in this dark energy-dominated future approach what some physicists calculate as a de Sitter temperature, a minimum temperature set by the cosmological horizon. This is a tiny but non-zero temperature associated with the quantum fluctuations at the edge of our observable universe. In a universe dominated by dark energy, absolute zero is never reached. The horizon itself radiates a tiny temperature, analogous to Hawking radiation from a black hole. The universe, in its final dark energy-dominated state, may settle not at absolute zero, but at a minimum floor temperature of around 10 to the negative 30 Kelvin. That's 1 divided by 10 to the 30th power, a number so close to zero that no human comparison can capture how small it is. Not quite zero, but functionally indistinguishable from it. Let's come back to something solid. Let's come back to the question that might be at the back of your mind throughout all of this. All right, space is cold. Deep space is almost unimaginably cold. But we keep sending things up there. We keep building telescopes and probes and planning missions. How do we manage it? The short answer is, very carefully, and with systems designed specifically for each mission profile. The thermal environment of low Earth orbit is radically different from the thermal environment of deep space beyond the heliosphere, and both are different from the thermal environment of the lunar surface. There's no single solution. There's a practice of thermal engineering that involves choosing materials, designing surfaces, routing heat pipes, selecting heaters, and validating everything in thermal vacuum chambers before launch. A thermal vacuum chamber is exactly what it sounds like. A large sealed chamber from which the air is pumped out and which can be cooled to simulate the cold of space and heated to simulate exposure to sunlight. Large spacecraft thermal test chambers can be several stories tall. The spacecraft is suspended inside on a special mounting structure, and the chamber walls are cooled with liquid nitrogen to about 77 Kelvin, which is negative 196 degrees Celsius, close enough to the cold of deep space to be a reasonable test. Simulated sunlight from large xenon lamps floods the spacecraft from various angles, and then engineers watch. They measure temperatures at hundreds of points around the spacecraft. They verify that heating and cooling happen in the patterns the models predicted. They look for unexpected hotspots or cold spots. They fix what's wrong. Then they launch. The margin for error is slim. The James Webb Space Telescope's deployment, which involved unfolding a sunshield the size of a tennis court and deploying a mirror made of 18 individually adjustable segments, had 344 single points of failure. Any one of those steps could have failed, and the telescope would have been useless. The whole mission depended on 344 sequential mechanical operations, all working correctly in the cold vacuum of space, 1,000,000 miles from Earth, with no possibility of a repair mission. It worked, every single step, but that fact doesn't erase the knowledge that it nearly didn't have to. Now let's talk about something that deserves more attention than it usually gets: the psychological and physiological effect of cold on the humans we send to space. Astronauts on the International Space Station don't experience the 2.7 Kelvin of deep space directly. The station maintains an interior temperature of about 22 degrees Celsius. Comfortable. Like a climate-controlled office, but they are always aware of what's on the other side of the hull. A hull that is centimeters thick. On the sunlit side, the exterior can be 150 degrees Celsius. On the shadow side, negative 150 degrees Celsius. The interior comfort exists in a narrow engineered bubble between these extremes, maintained by thermal control loops, fans and heat exchangers. If the thermal control system failed completely, the interior temperature would begin swinging toward the extremes within hours. There are documented cases of equipment failures on the ISS that led to temporary thermal management challenges. In 2018, a small hole was found in a Soyuz spacecraft docked to the station, causing a slow air leak. The station's thermal environment was not directly compromised, but the incident illustrated how thin the margins are. A few centimeters of metal and polymer between you and a thermal environment that would kill you in minutes without protection. Astronauts on long-duration missions also deal with cold indirectly through the effect of the space environment on their bodies. The microgravity environment causes fluid shifts in the body. Blood pools towards the head. The spine elongates as the discs between vertebrae expand without gravity compression. Bone density decreases because the skeleton isn't bearing weight. These aren't thermal effects, but they illustrate how complete the challenge of surviving in space is. The body didn't evolve for it. Everything about the space environment, the radiation, the microgravity, the thermal extremes, runs contrary to what human biology was built for. We survive out there by the grace of engineering. Let's now go to one of the most interesting thermal phenomena in the solar system. One that happens on a moon you might know about. Let's talk about Enceladus. Enceladus is a moon of Saturn. It's small, about 500 kilometers across, roughly the size of Arizona. The surface is covered in ice. The average surface temperature, far from Saturn and in the outer solar system, is around negative 198 degrees Celsius, or 75 Kelvin. Cold, very cold. But the Cassini spacecraft, which orbited Saturn from 2004 to 2017, discovered something that nobody expected. Enceladus has geysers, plumes of water vapor and ice particles shooting up from fractures near the South Pole, venting into space with force. At negative 198 degrees Celsius on the surface, there are active water geysers. Underneath the ice shell of Enceladus is a global ocean of liquid water. kept liquid not by sunlight, which is far too dim out at Saturn's distance, but by tidal heating. Saturn's gravity flexes Enceladus as it orbits, the same way you generate heat by bending a wire back and forth. The flexing creates friction inside the Moon, generating heat. This heat keeps the subsurface ocean liquid. The geysers are where that ocean water vents through fractures to the surface and blasts out into space. Cassini flew through those plumes, and it found organic molecules, complex carbon compounds, silica nanoparticles that form only in water above about 90 degrees Celsius, suggesting hydrothermal vents on the seafloor, molecular hydrogen, which is a byproduct of water reacting with rock at high temperature. Everything we need for the kind of chemistry that could support life. In an ocean that exists because of tidal heating in the outer solar system, in a place where the surface temperature is 75 Kelvin and space is at 2.7 Kelvin, there is potentially a warm, chemically rich, liquid water environment. The cold of the outer solar system is not uniform. Tidal heating carves out exceptions. Warm pockets in a cold universe, heated by gravity, maintained by orbital mechanics, possibly hosting chemistry that echoes the chemistry of life. The same is likely true of Europa, Jupiter's ice moon, and possibly Titan, Saturn's largest moon, though its potential chemistry would be very different, using liquid methane instead of water at temperatures around negative 179 degrees Celsius. Titan is a cold orange world where it rains liquid methane, where rivers and lakes of liquid methane carve channels in ice, where the temperature is cold enough that familiar chemistry, carbon-based chemistry, dissolved in water, can't work. But could there be chemistry we haven't thought of using liquid methane as the solvent operating at 94 Kelvin? We don't know. The question is open. Let's talk for a moment about what cold means in the context of extreme stars. Because we've talked about neutron stars, but there's something even more extreme. When the most massive stars die, something more extreme than a neutron star forms. If the collapsing core is more than about 3 solar masses, not even the quantum pressure of tightly packed neutrons can halt the collapse. Gravity wins. The core collapses past neutron star density through a threshold where the escape velocity exceeds the speed of light. A black hole forms. A black hole itself has no surface temperature in the ordinary sense. It has no surface you can put a thermometer on, but it has something else. Stephen Hawking showed in 1974 that quantum effects at the event horizon caused the black hole to emit radiation, now called Hawking radiation. This radiation has a temperature, and it's cold. Most people think the coldest things are in deep space. Some of them are. But the coldest temperatures ever created by humans are in laboratories on Earth, closer to absolute zero than anything in the natural cosmos. We've made things colder than the universe makes. Most people haven't thought about what the background temperature of 2.7 Kelvin actually is. It's the stretched and cooled remnant of the first light of the universe, still filling all of space, arriving from every direction, containing in its tiny variations the seeds of everything that exists. It is the oldest persistent thing we can measure, and it's cooling. Every trillion years, a little colder. On a one-way road to absolute zero that will never quite arrive. And most people have never thought about what the cold of the universe means for us personally. We are right now warm pockets in a cold universe. The warmth in our bodies represents a local, temporary defiance of the entropy gradient. We are not apart from the cold. We are surrounded by it, built from matter that has experienced it. sustained by a star that resists it, and headed eventually back into it. That is not a sad fact. It's just the full picture. And knowing the full picture is why we do this. There's a question this whole story raises. And it's the question I'd leave you with. We know the universe is expanding. We know it's cooling. We know the stars will eventually go out. We know entropy increases. But we also know that locally, temporarily, against the global trend, complexity emerges. Life emerges. Thought emerges. A star forms out of cold gas. A planet forms around it. Water appears. Chemistry organizes. Something learns to look at the sky and ask questions. The cold universe produces, in specific places and specific times, the complete opposite of cold and simple. The opposite of entropy. Islands of order in a cooling sea. How rare is this? How long does it last? Are there other islands? Do they ever find each other? These are the questions that the cold of the universe points toward. Not answers, but the shape of what we don't yet know. And if that question pulls at you the same way it pulls at me, the next video right here goes even deeper into the structure of the universe and what it tells us about whether we're alone in it.